We're really excited for a panel on data science and education, and we've got an amazing panel lined up, folks from Berkeley, Chicago, Columbia, our own Harvard and Toronto. And before kicking things off, I thought I would just take a moment to reflect on why I think that this is exciting. People have been out doing data science for a little bit now. It's a big and growing community. But way too often, I think, when people get together to talk about data science, we talk about data science, and we don't talk about how to teach data science. And I think this is an opportunity that this panel represents. It's also an opportunity, I would say, that just different efforts at Harvard and elsewhere that really trying to catalyze that particular conversation. So the fact that the Harvard Data Science Review actually has an explicit mandate and an explicit co-editor, that's something. They did not necessarily have to go that way, and I think it's a testament that they did. Harvard's own Data Science Initiative has been regularly convening events. They have this industry speaker series, so if you're from Harvard and you're not on that mailing list, you should be, because it's a great opportunity to see how these things play out in the real world. And then in the provost office, even at Harvard, there are efforts in that regard. So I'm really excited for today's panel. My name is Dustin Tingley. I'm the Deputy Vice Provost for Advances in Learning and a Professor of Government. And I found out a couple years ago that I'm a data scientist too. We're gonna kick it off with the folks from Berkeley. So I'd like to welcome Michael Jordan and Ani Adhikari up for their presentation. Slides.
It's upside down, so that's us. Thanks, Dustin. We started, at Berkeley, we started on this journey some years ago now. 2014 seems like a long time ago. Many of you will know that we have an introductory class for students who have absolutely no background, and we have made it open, and there's been a lot of buzz about that, but for us, that was only a starting point. We started with a picture of what we wanted data science education to be at Berkeley, and that did involve all students being able to reason sensibly based on data, make decisions based on data, everybody, regardless of background. And it did involve a blend of concepts, blend of statistics and computer science, the best of both. So from computer science, modularity, scalability, abstraction, and from statistics, inference, uncertainty, quantifying uncertainty, understanding the model, the importance of the model, respecting the domain from which the data come, interpreting the results. So this is statistics and computer science with an outward-looking component, which is that we wanted it to be very tied to all other domains. And we wanted students of any background to be able to do something significant. So the student sees that they're not working with 11 red balls and 5 green balls, but they're actually doing something. They're answering a question that is interesting to them and that matters to them. But more than that, we wanted the same thing for all students regardless of background, and that means the students who had considerable background should also be able to go as deeply as they want. And so that's really what we want to talk about today, which is not just the foundations course, but what this looks like now that we've had 3 or 4 years to put it together. And so it does indeed start with a foundations class where the students come in with no math and no programming, and we introduce them to Python, and we introduce them to the ideas of data visualization, descriptive statistics, and inference. They are encouraged to take what I call connector courses. These are courses in other disciplines that they can take simultaneously or after the foundations course, and these are typically small sort of seminar-style classes where in the domain you analyze a particular question. So you analyze data in a domain, in a seminar-style setting. And once they have done that, many students report a life-changing experience. People come in thinking, I don't know what this is. There's a buzz. It kind of sounds cool. I'll do it. And then at the end of that, they're surprised that they want to continue. Now, we ask them to continue by thinking about the human context around data, that it is not merely a computational game, but that they have to think about issues of fairness, bias, and so on. And so there are numerous courses, including a couple of new ones, which address exactly this issue. There is, I think there's a course called The Moral Context of Data Science offered by the Philosophy Department, and there's a course offered by History and the School of Information, and so on. And now, of course, if you want to continue going, you need a little bit of underlying skill, and so they are encouraged to take a little bit more math and a little bit of computing. So it's a little bit of calculus, a little bit of linear algebra, and to actually be able to write a Python program. So our introductory Python course is very, very popular. Having done that, they are a large number of them take the next step and go to the next course, which we call Data 100, and that is a class which starts out by actually teaching students how to wrangle the data, right? The thing that data scientists spend quite a lot of their time doing. So there's drawing the data from various sources, putting it together, and then thinking about the life cycle. You have a question, you're trying to answer it, how do you gather the data? How do you clean it up so you can work with it? And then how do you address the data? What are the questions that you can ask? What are the questions that you can answer? And what can you interpret? This is all done, the probability is at there's a very light touch. The probability is done rather lightly here. And students are introduced to multivariable analyses, which they aren't so much in the foundations course. So, they do a bit of gradient descent, they do some multiple regression, they do some logistic regression, clustering, and so on and so forth. And at this point, the student is almost done, well, they have a couple more elective courses to get what we call a data science minor degree. So in addition to their main concentration, this is a smaller area of emphasis that they can have. And so they can get that with a little more math. If you want to go deeper, you have to understand the probabilistic underpinnings. And so this is a class which, on the one hand, looks like a traditional probability class and also interleaves computation and mathematics, just as all our other classes do. Students come into these classes highly motivated because from Data 8, they have a very sharp idea of the shapes of distributions. Which ones look like which? Why? Which ones are bell-shaped, which ones aren't? And so you have highly motivated students coming in, very interested in the questions, and this class introduces quite a lot of inference as well, the maximum likelihood world, the Bayesian world, and so on. And then you put it all together into a course that we call Data, Inference, and Decisions, and Mike will talk about that. While he's getting up, let me point out that we've gotten sensible about the names. Everything doesn't say for data science anymore, but the numbers are ridiculous because we had to find a number that worked both with computer science and stat, and there weren't any left.
Okay, so from the beginning of this 5-year process, it was critical to us to think about making students come out and thinking. So this was not about skills. I know a lot of data science is about a skill set. You got to be able to run this software and run this pipeline and set it up, and that's very important. But we wanted to get them that skill as part of something bigger. The bigger thing is you come in the room later in life and you're being asked to solve a problem. And the problem is usually a little bit vague. It's out there in the real world and involves collecting some things, it involves thinking about what you're going to try to achieve, what you can achieve. It involves the team you're going to put together to do that. It's all about the thinking. So early on, we had this buzzword, computational thinking and inferential thinking. That was a nod to the fact that computational thinking already existed as a buzzword and it was being used for everything. That's all there is, isn't it? It's all the computer. Well, no, there's this 300-year tradition of inferential thinking, so we highlighted that. But it's all about the thinking, okay? And so why? Well, because this stuff is not just about tools to go out there and run, it's about to go out in the real world where things are consequential. Medical decisions, commerce decisions, financial decisions, human welfare decisions, it's consequential. A lot of this data science was developed by companies that are sitting behind a search box or behind a social network or behind an advertising platform, and there's no consequences except they make a lot of money. Right? That's not the future. Okay, so this is as much about pattern recognition and vast amounts of data and storing it, moving around and all that. That's part of it. That's kind of the first half. Really, the more important half is the decisions coming after that, right? Decisions. Decisions, even one that's consequential like your own medical care, it takes time. It takes multiple data sets. It takes what-if questions. It takes error bars. It takes consultations. It takes dialogues. But it's never one decision. It's always a bunch of decisions you're making in the context of other people and scarcity and economic considerations and social science considerations and so on. So our final class, called Data Inference and Decisions, this was the one we had in mind from the very beginning. This is meant to launch people into a career where they're the thinkers in the room, not just the executors. Okay, so I wanted to show you the syllabus. This is a crazy thing to do, but this is our last slide, all right? But this is our syllabus. No statistician or computer science will recognize more than half of the stuff on here. Half of this stuff is advanced grad stuff that's never been taught in any class, all right? But it's core to thinking about decision-making problems in real contexts involving other decision makers and scarcity out in real life. False discovery rate is a big statistical idea, but the real problem is doing it at scale in an online setting. That any given moment, I'm going to stop a decision maker and say, how many decisions you made up until now? How many of them are good ones? That's a new problem. There's only the first research paper about that was about 3 years ago. You can teach it at this level because it's a simple, core, great idea, and there's an Erdős-style proof for it. It works because there's a simple proof you can do in 3 lines. So we worked up to that, and after the first 5 lectures, they get to that proof, they understand the algorithm, they can implement it, and they can try it on real data, and they love it because it's so cool. It's not a standard algorithm in any textbook. And then we go to a little bit probability. We get towards causal inference. The thing we're working up to there is things like bandit algorithms, where you're trying to make decisions in the real world that are noisy. You don't know what's the right decision. No one's telling you. You have to do some exploration. How do you trade off exploration and exploitation? Then we bring in some microeconomic concepts and some control theory concepts, because you need them if you're really building real world systems. This looks like a super duper graduate curriculum. And some of my colleagues looked at it and they said, well, you know, just like with Data 8, you just did pure statistics, right? No. And here they're saying, well, you're doing this super advanced stuff. No, you can explain every one of those ideas in 10 minutes, and students love it. So I really want to encourage people to think out of the box. This is not about mashing up last generation statistics and computer science and a little sprinkling of social and a little this and that. It's rethinking the whole thing. And to me, decisions are the core part of it. That's why it's our final course.
That's the picture I was expecting to see, right? Is that your picture?
You could bump us out.
All right. Let's see. So where am I? Do I just keep just advancing? Great. Okay. So great. So Mike Franklin from University of Chicago, and we're I would say quite a bit. Or let me say it slightly differently, we're not nearly as far along our journey in teaching data science as my colleagues, my former colleagues at Berkeley are, and we've been watching them with great interest and great admiration, actually, for all the things they've been doing, and we've been very much inspired by it. The context at UChicago is really one of just massive growth. There's been an explosion of interest. I'm sure mostly where you guys are from as well, but really across campus in terms of people realizing that data science is just crucial for their fields. It's having a fundamental effect on how people do cutting-edge research in their fields and in how they need to be training their students for further study and for their careers. And so we've been hiring lots of really interesting people all around campus. Computer science has basically doubled the size of the faculty in 4 years, but also beyond computer science, many other places on campus, the business school, economics, and so on, are bringing in very, very data-centric people. So that's part of what we're doing. That'll be my first advertisement that we're hiring. We're looking specifically for database people. Sorry, that was a Freudian slip. Data science people. So one of the first things we did was we created something called the Center for Data and Computing, and we put out a call for seed grants around campus. We got proposals from every unit on campus except for the Divinity School. We have a new call out right now. We're hoping the Divinity School contributes to that one. But if you just, it's a bit of an eye chart, but if you just scan the topics, of the types of research that people are doing, the rule for these proposals was you had to have methodology people and domain people working together, and you had to be able to argue that the research was going to advance both the domain and methodology, and we got just a huge outpouring of interest and lots of really interesting projects going. So that's part of it. Now, when Dustin introduced the session, he said, you know, we spend a lot of time talking about what is data science, but we don't talk much about how you teach data science. There's some truth to that, but I believe, and I think my colleagues at Chicago believe, you really have to understand what is data science, or at least start approaching that question in order to be able to teach it effectively. And so we put together a group of people from around campus, and the first question that we asked that group was, you know, do you believe that we can teach data science? There's no question everybody knew we had to teach data science. But the question was, should we just take you know, some things from computer science, some things from statistics, some things from, you know, whatever domain is relevant, and put that all together? Some of you might recognize this is one of the original Venn diagrams to explain what data science is, as data science was just starting to emerge as a term. And so we asked this group of interdisciplinary people, you know, is this what it looks like? Or do we believe that there's really an emerging new discipline forming? Is there something new happening here that we need to think about from an intellectual point of view and try to figure out how to approach that? And I thought that we were going to spend, you know, the first 2 months of that committee talking about that question, and the answer came out in about 15 minutes. And people from all over campus said, no, clearly there's something new going on here. It's not just taking some old ideas, as Mike was saying, from a few existing fields, but really we need to start thinking holistically about what is a new discipline of data science. And yes, we have to think about how to teach that to people, especially undergraduates, because they need to know this stuff now. But as you know, at a research university, in order to have a program that's got real heft, there has to be a research agenda, and there have to be a group of people around campus who are committed to pursuing that research agenda. Otherwise, the field isn't going to gel as a field. The Data Science Review is one example that things are starting to gel once you start getting you know, journals and things dedicated to a topic. But we took a step back and we said, okay, well, what would this new field look like? And we came up with this admittedly, you know, bit of a cartoonish icon. But the idea here is that you want to think about things holistically. And yes, there's computer science and machine learning and statistics and domain sciences, but there's a bunch of other things too. Communication was one of the topics of the previous session. How do you help people make decisions with data? How do you communicate enough so that you or other people can make decisions? Societal implications of data and data science, obviously that's been underlying all the discussions today. And this other bucket that we called missing foundations, which was basically asking the question that if we believe there's a new discipline emerging here, what are the questions that either aren't being asked because they fall between the cracks of the existing silos, or, you know, what are questions just simply aren't getting enough attention or the right attention? And so we came up with a list of those, and I'll just show that to you towards the end of my remarks. But underlying our approach is this idea of a data science life cycle, and the idea that it's not just machine learning, it's not just analysis, it's not even just data wrangling, but it's an entire process of trying to understand what are the questions you're trying to ask and answer, what's the data that you need to effectively be able to answer those questions, how do you get that data, and then how do you process it all along the way. And, you know, this is a picture from a study that Fran Berman, who's sitting in the middle of the row there, she led a study for the National Science Foundation Computer Directorate, and trying to answer some of these questions about what is this new field of data science. That group of people came up with this particular representation, but the important thing is it is a life cycle that goes from experimental design all the way through curation and understanding what to do with data products after they've been created, and that there's a cross-cutting set of concerns that have come up, over and over again in our discussions here. Ethics, policy, regulation, stewardship, and so on. And so when we're thinking about teaching data science, this is our mental framework. We want to teach the whole thing, not just points along the way. Now, in order to make some progress, we started off with a data science minor. A key thing is that it's a joint effort between computer science and statistics. This is something I learned when I was at Berkeley, that you're just not going to be able to build an effective data science effort if you don't have buy-in from both of those communities, as well as lots of other people on campuses. So from day one, we agreed that it would be a joint effort spearheaded by computer science and statistics and bringing in as many other people as we could. Now, interestingly, when we went to create the minor, what we found is we actually didn't have many of the classes that we need. In fact, in order to create a 6-course minor, we had to create 5 classes. And that might say maybe more about where we were as an institution when we started, but I think that's probably true of a lot of places. And so the courses that we teach are, we have an introductory sequence. We're on quarters, so we either have to do 10 weeks or 20 weeks. And so that gives us the ability to cover quite a bit of material, but we do require people to take 2 classes if they want to go through the whole program. And so in the first class, we follow the Data 8 textbook and we use the Data 8 tools, which are, the way to think about it is sort of data science with training wheels on. And in the second of the sequence, we take those training wheels off and we teach them using the real tools that they're going to use when they're doing data science, or at least tools that they could be using in the real world. That sequence is currently being taught by myself. I'm the chair of computer science, and my colleague who's the chair of, Dan Nicolai is chair of statistics. So it's an interesting combination. And we had to create courses in data engineering, and responsible data science and ethics, background for machine learning, and so on. And those are the classes we ended up creating. I'm going to skip that because I'm running out of time. But if you want to talk about research topics and data science, I'm happy to do that. But the main point is we want to treat data science as an emerging discipline. We believe it is an emerging discipline, and we want to think about what does that mean for undergraduate teaching, as well as for professional education and for research and for PhD education. So we're building out a major. I'll say it again, we're hiring in data science. We have job openings that are specifically targeted to bring that first group of people that's going to come to campus with the goal of building a data science program. And they'll end up in CS or in stats or in some other department, but they're going to come in the door knowing that they're part of this cadre of people who are going to help build this program. We're actively building out a data science research agenda and the support that needs to go along with that in terms of collaborations. And part of that is going to be having a PhD program. Now, I just mentioned quickly, having a PhD program in data science is different than providing PhD students with the training in data science methods that they need to do their research. And so we need to be thinking about both of those things and who's going to be doing them. So with that, I will yield the microphone.
Great, thank you very much. Next up, we have Alison Gibbs from the University of Toronto.
Oh, that's not what that slide's supposed to look like. So there was a bit of a, I'll tell you what it's supposed to look like. I've got to stand still. I learned that in the last session that with the mic. So thanks very much. Thanks to Xiaoli for the invitation. It's a real pleasure to be part of this this conversation. The title here that somehow got separated is Navigating Whitewater. And the subtitle is Undergraduate Statistics Education in the Era of Data Science. So I'm a statistician. I teach in the statistics department. We have a lot of students, which I'll address in a minute. Until very recently, I was leading our undergraduate program. And so I chose to take the gift of this time to to speak a little more conceptually than the previous speakers, but give a lens well, two things, I think, an analogy and perhaps a model for our graduate from our statistics programs of study that is strongly influenced by our students and data science. So hopefully the rest of these slides are gonna, no. Okay, strange. A lot of people have been experiencing a lot of growth in their programs of study. This is the growth in statistics programs of study at the University of Toronto. The purple line is all, so students register in their program of study after first year. So these are students in second, third, or fourth year. In statistics, as you can see, it was pretty stable after a while, and then something started happening around the 2010 mark. And then just in case that scale hasn't been emphasized enough, I want to note that these last year's numbers came in at just under 4,500 students as the total number of students. So that's a lot. And the typical question we get next is why? What's attracting all these students to our programs of study? And I think the short answer is the good press, in particular, a lot of excitement around data science. So if we look at where the growth started, it was right at the time that the famous Halvarian quote about statistics becoming sexy, and then as we see when it really started accelerating, the quote from Harvard Business Review about data science being the sexiest job of the 21st century, and it really took off from there. And when we asked our students why they were interested in taking a statistics program of study, these are their responses, with the top ones being the most commonly responded ones. And to summarize, it's interesting, or we can solve interesting problems because it's useful. And the one I thought was interesting is then what comes in third is because it complements what else we're doing. I think that's a reflection of the students we've got. They're quite an extroverted group, and I think they're different than somebody like me, who was probably a typical statistician from a previous generation who did an undergraduate degree in mathematics, saw some light that I wanted to work on some things that had some applications to the real world, and found my path through statistics. Our students are thinking from a data-centric point of view, and whatever else they're thinking about the importance of statistics in order to help them with those problems. And just to emphasize that perspective again, the programs of study that have the fastest growth, which are the blue line and the orange line, are students that are combining statistics with study in another discipline. Some of them are computer science. Some of them are combining it with all kinds of different things across campus. But again, they're not the traditional, or at least from a previous generation of statisticians with starting off with mathematical training. They're much more extroverted. So this is my analogy for what's been going on a bit. It's a bit like paddling in whitewater. So whitewater's a lot of fun. You can prepare all you want, but you've got to be ready for constant change with the changing river. That sort of describes how we've been dealing with this rapid growth in our enrollment. But I think it's also a really good analogy for our programs of study and what we want our students to gain from them. We want our students to be able to navigate whitewater. We want them to be ready for a world that's constantly changing that they can adapt to. We don't want them to be too rigid and follow just the rules. As I can personally attest to, that can lead to disaster in a whitewater situation. So they need to have a sense of play when they're approaching the river. They, at very crucial moments, they need to be more innovative. And so we need a program that gets them moving in that way, because I think that's reflective of the data science world, is some agility and some nimbleness. Which brings me to sort of the model that I've been thinking about a lot for the habits of mind that we want our students to have when they finish our statistics programs of study, and changes we've been trying to implement throughout the program in order to develop these habits of mind. And the model is an adaptive expert. So an adaptive expert has two features. They're first of all an expert. So again, I'm talking about statistics students. So they're they've committed to a program of study of statistics. So they're committed to being an expert in some sense of the data science world. In order to be experts, they need to have extensive knowledge that they can apply efficiently when they've seen problems before. That's roughly the definition of an expert. But in order to be an adaptive expert, which we're working on developing with them as we head them out into the data science world, is that they can take that expertise and apply their knowledge in novel, complex situations, create new procedures when necessary. They're much more flexible. They're continuous learners. That's just the way they approach everything. They seek challenges. And in order to do all this, they have to have well-developed metacognitive skills so that they know when they don't know and when they need to learn and so on. And there's some nice literature in adaptive expertise that gives some good advice about how to do this. It started off in elementary education, but fairly recently it's been adopted by, in professional settings, engineering and medicine in particular. Key ideas are that we need to spend more time on giving them, in particular that middle box is where we've been thinking a lot, is opportunities to explore, discover, and struggle. And part of that, and part of a curriculum that rewards that, that kind of work, not just the outcome. So I'm not going to go into depth in that. We've got a first course in data science, again, for people coming in with no background whatsoever as well. It's different than the courses we've heard about before in that it's not a joint endeavor with computer science. Our students in our statistics program of study also take, Computer Science 101 from our really excellent computer science department, but well, computing's still a major part of that course, but we like to think of it as teaching them to code by stealth. That they're motivated by a problem and that they need the coding in order to solve it, and so they kind of learn coding whether or not they want to as part of the process. But a couple of things I wanted to point out about this in terms of the development of adaptive expertise is, of course, it's necessary to pay attention to that. So the bar on the left, which we had described as Mondays, because that's how the course is structured, and the bar on the right with Fridays, is equal time. The Mondays is a big group session, and the Fridays is small groups. 20 students, which University of Toronto being as large as it is, 20 students rather, is quite a small group. But that's where the real adaptive expertise is built, and it's built through communication exercises. A lot of it is making the students think about and articulate, emphasis on the articulation of why and what happens when, and what if I do this, what happens next, and when does this work and when does it not work, and what would we do if we were presented with this different situation. One of my favorite questions to ask is, well, what if I gave you this new setting? Maybe you don't have everything you need to solve it. What would you ask in order to get there? And again, equal time is the emphasis there, that in order to make that happen, there's got to be a serious commitment to that time. And it wraps up with a project. If you're wondering how you get, we put 1,000 students a year through this course, and they have a big poster fair, low-tech posters, to present their findings. So just to maybe one more slide. The data science Venn diagram came up earlier, and just to expand this a bit more into our programs of study and how we're thinking about them, is we've been through a big curriculum renewal exercise, and the faculty all involved in what it's important for our students to know and what they can do and how they think when they get out of our programs of study. And for statistics, what we saw was this kind of squishing together. Is, the original data science Venn diagram that we saw a few minutes ago, had the statistics and mathematics and had the computational thinking and had the domain expertise. And we're trying to bring those the other aspects much more into our statistics program of study to prepare our students for the data science world. Certainly, we think that's what they want, and that's why they came to the statistics and why we have so many students. So, that's our big mission statement for our program, but I think I'll stop there and use my time. So, thanks.
Thank you very much. Up next, we've got Joe Blitzstein from Harvard University.
Hi, thanks Dustin, and thanks everyone for coming. I didn't make slides, which might have been a horrible mistake, but at least I don't have to worry about whether they display properly. And also, if I had, a bunch of my slides would have been quite similar to ones we've just seen. You don't need to see the data science Venn diagram a third time. And but I mean in a good way, because like there were so many things in the talks just now that resonated more than I would have expected with my own experiences and our own experiences here. So I just wanted to talk briefly about, what have we been doing in terms of data science courses at Harvard. So Hans-Peter Pfister, who's from computer science here, and I'm in statistics. We taught Harvard's first data science course, and by which I mean data science is the title. I don't want to debate what is data science, which is very interesting, but would take much more than 10 minutes and not the topic of the session. We taught that course back in 2013, and I would say it was by far, we co-taught it. It was by far my biggest pedagogical challenge ever. The logistics were incredibly complicated. There was no suitable textbook. There have been more and more good books coming out recently, but there was no standard curriculum, no books. We wanted to cover the entire data science life cycle, right? That Michael F. was talking about. And we wanted to do all of that in one semester. So that was a huge challenge, just in terms of trying to, because as Xiaoli was talking about at some point earlier, there's always these depth versus breadth trade-offs, which applies in both research and teaching. And in this case, like, we wanted to cover that entire life cycle or the entire pipeline, but there's a major risk if you do that of being very superficial about each thing there. Each thing in that pipeline could be, and often is, an entire course in its own right. We want to do all of that in one semester, and it went okay, but I still felt like we were rushing from topic to topic way too much, and we wanted to have more depth and more breadth and everything, but sometimes there's trade-offs there. So one way we resolved that is to expand it into a full year sequence, and for that sequence, both semesters are co-taught by computer science and statistics, and we've seen some examples both ways, whether courses, purely in one department or co-taught. But we thought that was very important that be a partnership between CS and statistics, partly just for the message of, that data science is an emerging field, but it involves a lot of CS and a lot of statistics. Personally, I didn't feel competent to teach that on my own, and Hans-Peter didn't either, and it was fun. Like, I learned a lot. He specializes in visualization, which is extremely important in statistics, but rarely gets taught in statistics. So I learned a lot from him, and hopefully he learned a few things from me. So anyway, we did it that way, which was actually a challenge, and I don't want to get into all the too Harvard-specific things, but there was not a good way to cross-list it as both statistics and CS. But we thought it was so important that this is equally a statistics course and a CS course that even though there was no mechanism for doing that, we just listed it twice as if it was two separate courses in the registrar's eyes, which is a little bit of a hackish solution to that. It's gotten a little better since then. The other pedagogical challenge there was that the students we had, the first time we taught it, we already had 400 students just show up, and they were all, I should talk about prerequisites. So for this course, unlike Data 8 at Berkeley, which has no prerequisites, this course we assumed intro programming and intro statistics. So it could be like high school level, like AP statistics, AP computer science, but some basic programming and statistics that we were requiring there. But despite that, since we had 400 students, they were all over the map in terms of their backgrounds and interests. So I'm used to teaching probability to hundreds of students where there's a very, very wide spectrum in terms of their mathematical preparation, which is a challenge, but at least I felt like that's a one-dimensional thing. It's just like less math to more math, and you can find ways to kind of layer the lectures and the homework so that, almost everyone hopefully gets something out of it, but the best students are not bored and so on. Here we're in this like three-dimensional space of different backgrounds, so that people have had lots of programming, but no statistics, and people who are very mathematically strong, but had never run a linear regression, and there's this big space of different backgrounds. So that was a very interesting challenge, and that we're still working on. But I also wanted to talk about the new thing that we've been working on. So last year, Harvard Faculty of Arts and Sciences, voted to approve a new requirement for all Harvard College students to have to take a course on quantitative reasoning with data. And there was a big debate. I'm not going to go into the politics here. There was a big debate about whether data should be included in that. Should it just be quantitative reasoning as sort of a gen ed type thing, or quantitative reasoning with data? Faculty voted that there will be quantitative reasoning with data. So Xiaoli and Hans-Peter and Liberty Wittert and I and Alan Downey, who's visiting this semester, have been developing a course which is more like Data 8, where it's data science with no prerequisites. And the Data 8 has been a great inspiration for that, but we don't want to just copy it. We want to add our own innovations and do our own thing too. So just for my last couple of minutes, I want to briefly, this course has not been taught yet. We're going to be offering it for the first time in the spring. So if we have a follow-up, a year from now, we can tell you how it actually went. But in terms of what we've been working on this semester, we want to focus it on case studies. So for the course that Hans-Peter and I taught, I think we did a pretty good job covering a lot of statistics, machine learning, and CS ideas. But in terms of that Venn diagram, what was really missing was the domain knowledge. So after teaching that course, Hans-Peter and I started teaching a business school course with Shrikant Datar from the business school as part of the Harvard Business Analytics program. We have a few of our students from that program here. And the great thing there was we added the domain, which in that case was business. So that course has been really fun to teach. So now that we're designing the one that's for Harvard College students, we're trying to take the same idea where it's based on case studies, like business school case studies, except making it into data science case studies. And of course, some of them can be business. Harvard does not have a business major, although hundreds of Harvard students would love it if such a thing existed. But it's not. So we're taking case studies that could be anything, like predicting elections, movie recommendations. We have a case study that we're working on about sleep, and just all kinds of interesting topics. The Google flu trends was another really interesting example. So we're currently developing a lot of those cases. And then a big debate that we had, in deciding, how to structure this was so the idea of the case is you have this really rich, exciting example where everyone can see why this is important, why data science is important. And in each of these cases, you can trace through the entire data science, pipeline, the whole process for each one. But again, could that be too challenging? And we didn't want it to be just data literacy. We want our students to be able to leave the course feeling empowered, like they have skills. And if we only did the cases, it could seem too challenging, and then we're not teaching them the foundational skills. So we had this debate basically between top-down and bottom-up approaches. Start with basic things like for loops and confidence intervals, and slowly work your way up. And you might never get up to these really rich cases, or start with the cases, but then they can sort of read them, but they couldn't really implement something like that themselves. So what we're trying, and we'll have to see how it goes, is we're teaching Monday, Wednesday, and Friday. Monday, we're focusing on the case studies, which is very top-down. Wednesdays, we're going to focus on the methodology and much more bottom-up of just here are the key statistical and computational methods and thinking that you would need in order to do that kind of case yourself. And then Fridays will be much more hands-on, labs, where everyone is just implementing it on their own computers and trying out those things. So that's what we're trying there, and I've used up my time, so thank you.
Last but not least, we have Matthew Jones from Columbia University.
Did anyone try reasoning with big data?
Great. Thank you for having me. A lot of what I'm going to say is going to have echoes with things other people said, though our strategy, I think, and concerns is slightly different. So I'm going to talk today about a class that I've devised and co-teach with Chris Wiggins, also at Columbia and the chief data scientist of the New York Times. And unlike many of you, we're not in CS or statistics, so we can think about both of your houses, but we're slightly askew. Now, our class is called Data, Past, Present, and Future, but because we're working at an Ivy League institution that has certain attitudes about what its students are supposed to do, a way to think about it is, what should future statisticians, CEOs, and senators know about the history and ethics of data? And I'm going to talk about the hypotheses behind this class, why we talk about ethics, and then I'm going to give you a very quick survey of really our syllabus, sort of what Mike did and some of the things that we learned about it. But we began from a hypothesis that there was important material that is being taught neither to those who would see themselves as future senators or future statisticians, that both what Chris would call our fuzzy students and our techie students were lacking the kinds of critical education that we, as many liberal arts institutions, see as necessary for citizenship in the future. And we combined this sense of the lack in our curriculum with a sense that there was a lot that one can teach without prerequisite. And I've heard a lot of echoes about that there's considerable amounts of statistics and data science that can be taught from the ground up, particularly for students with less technical backgrounds. But likewise, there were important critical and rhetorical faculties that tend to be less present in technical domains that we also could teach. And this stemmed from both of our experience in teaching in various contexts where we say taught data science to aspiring data journalists and other sorts of things. So it was grounded in previous pedagogical experience, as well as experience that I have in doing sort of general education classes in moral theory and philosophy for all Columbia undergraduates. And then finally, we felt strongly that we wanted to pair intellectual changes with their political ethical context, to constantly ask questions about what powers motivated technological advances, and how did this advance rearrange power? In some sense, we wanted to get to the questions that so preoccupy many people in concerns about the critical questions about the data sciences in the present, with a broad understanding of the way that those questions have long been answered. So yeah, to quote The Onion, why history? Because historians remind nations to check what's happened in the past before making decisions. That history actually, far from being sort of, a boring domain that you might have to take, is profoundly actionable because it takes us back to when the kinds of decisions we are making today were made in the past and gets at their contingency. So why ethics? Well, we were interested, as many people are, with what is wrong and a whole sequence of studies that are important critical interventions in the domain. But studies that both more technologically motivated and more humanistically motivated students at once wanted to learn about and simultaneously look for the next stages about what are the solutions going to be. And hence, we just wanted a class that would look at ethics in a way that was profoundly important and useful for both our, as Chris would say, fuzzies and our techies. Now, what did we teach? The class is organized largely around the chronological development of the data sciences, beginning from the 1770s, the moment in which even the word statistics became to mean quantitative data about the state. And then we run through the history of mathematical statistics, regression testing, the massive introduction of computation that happened in World War II, the development of AI, and then finally getting to machine learning and the data sciences. And we teach, as it were, and the breadth of technological developments. And we have the possibility here to introduce those students without strong technical backgrounds to key notions such as regression and then more recent machine learning. But along the way, we constantly pair all of these technical developments with some things going on with my slides, with the question of how did these new capabilities rearrange power? Who is empowered and can ask questions differently and matter in the world differently? And what are the roles of rights, harms, and justice? So rather than getting to ethics and politics only at the end of the class, it is integrated throughout. So the moment we introduce regression, we also introduce where regression was coming from. So the way we teach the class is one day we have lecture and discussion, which introduces concepts, their history, and then critical reflection upon them. And then the subsequent day is a lab that we do in a Jupyter notebook using Python and the standard stack that other people have alluded to, pandas, scikit-learn, and these sorts of things. So we run through a whole series of topics from social physics, a la Ketley, the development of regression, the development of Bayesian theory, symbolic AI, and then the development of machine learning before turning fully to ethics and other sorts of things. And in our labs, which happen on Thursdays, we begin with the students doing a deep dive into a particular data set before learning how to do, say, EDA with pandas, and then moving through a whole series of sorts of things. Just to give you a sense of what this looks like, in week 3, we talk about the key moment in which a Belgian astronomer, Ketley, transformed the theory of errors into an understanding of human variation. And we understand the conditions, we'd get the students to understand how this intellectual leap mattered. We work with sort of this challenging text from a French historian that really makes the students think. They read Ketley, and then they do computation in the notebook to see how this works. The notebook integrates at once a close reading of the very metaphorical way in which Ketley did this with learning to do basic descriptive statistics. And we continue this. So in week 4, we look at regression, and the students then do regression. Right, and similarly for IQ, policy and causality, again. We look at the growth, the importance of signals intelligence and the computational imperative that began in the Second World War, and trace that in the development of subsequent machine learning. So I'm just giving you lots of examples. So in this one, the students actually follow a manuscript of Turing that was classified until quite recently, and they become Bayesian cryptologists, and they do this in the notebook. Yeah, and so here's an example. I'm sorry, I'm giving you so much. This is where we introduce them to, say, random forests. And when we introduce them to random forests, they both can learn this in a black box way, but I also read Brayman on forests being A+ predictors. But on interpretability, they rate an F. And to think about how that is, they need to have critical faculties about that, both at a technical domain and in thinking of ethical and political situations. Towards the end of the class, we turn more strictly to the ethics of data and look through many key examples. We give them the history of the Tuskegee experiments and the way that that became the crucial drive that drove the development of IRB and this sort of thing. In the lab, we actually create in real time a database of ruin, and we show that we can, through a large amount of information, isolate all the sorts of students. Now, so what did we learn? Well, this is a highly experimental course, and things didn't work from week to week. We had a lot of problems of the kinds that people have alluded to. For example, this is neither a statistics nor a CS class. In fact, I'm in a history department. Chris is in applied math and applied physics, so it's the only class on campus that is cross-listed history, applied math, and applied physics, which has no institutional home. It's incredibly challenging to staff because we need TAs that can work as easily in Python as they can with the French philosopher Michel Foucault. And yet, it's enormously exciting. We managed to convince our faculty with good conscience that for non-technical students, this was an excellent way to fulfill a science requirement. And for engineering students, this was a very important way for them to fulfill a humanities requirement in their sorts of things. We learned very much that if you tell the story of the development of data, of the data sciences as one of truth of power from the beginning, you create the conditions in which the students themselves can imagine how they are going to be the leaders to think about not just data for good in a kind of vague way, but that can pursue what I think many of my co-panelists have stressed, is that we are interested in producing leaders who are not sort of mechanically doing sorts of things, but that bring the full set of critical faculties that are needed to the applications in the data sciences. And those critical faculties may be as practitioners, and we had many students who were quite advanced machine learning students, as well as future leaders who will be working with such practitioners. Thank you.
Great, thank you, Matthew.
Oh, and for one last thing, all of our class material is available at this GitHub if you're so interested in seeing particularly the labs that we created.
Thank you. I know I want to go back to school. This just wasn't around. So we wanted to open it up for some questions from the audience. And so while you're all thinking about the amazing questions that you're about to ask, I thought I would just open it up with two related questions. And folks should just feel free to hop in as they please. And also, if something comes up, ask each other questions. That's totally game. But just a reminder that I'm about to be Oprah in a couple minutes and come out to the crowd with a microphone. So just please start thinking of the questions that you would like to ask. So my question is, we've heard a lot about what, not exclusively, but we've heard a lot about what we're doing around data science education at the undergraduate level. And that's super exciting. And I think that the sort of transformational moves that are being made, Berkeley kind of leading things off and others doing amazing things, that's great. But how are your schools thinking about data science education in any sort of systematic way within professional schools? And the reason I ask that is that these are folks who are coming in, there's a shorter timeline, less opportunity for electives. It seems to me very challenging. So I'm just curious how that, where you're seeing those conversations, what's been fruitful, how have your efforts been in the undergraduate world been helpful for the professional school space? And then the second question, and y'all can take either of these, is, not everyone's going to be a data science major, minor, concentrator, certificate, or whatever else. They're going to be working in other fields. How are we thinking about integrating your students into teams that are populated by poets, political scientists, economists that do a little bit more than the snippet at the end of the Data 102, et cetera? How are we thinking about the integration of teams? Because one of the things that I hear a lot from my colleagues at MIT is that employers love hiring their students because their students know how to work in cross-purpose teams, and Harvard students just know how to work on their own. And so I'm just wondering, how are we thinking about embedding data scientists into teams that don't include data scientists or even want to be data scientists? So I'll let anyone go, and expecting questions from the crowd momentarily.
Slightly off of what you're saying, but then I'll return to it. You presumably all know about the connector model at Berkeley, and I want to highlight that because that was the hardest thing we did in Data 8 from the very beginning. We had to walk around campus and find a whole bunch of people, it's up to over 20 now, in different departments who were willing to partner with us in the sense of they didn't get to teach the core class, but they taught a one-unit class around ours. That means we were not doing here's the case study, because we could do it, but we're not the world's expert on cosmology or law or cognitive science or biology. We wanted to empower our colleagues to feel like they were part of a team. And I think that that's the hardest thing to do on a campus, is to get that kind of thing going. Deans didn't want to give them credit for teaching a one-hour class and all of it. I just encourage everybody here to make your deans do that. It was the most healthy thing we could have possibly done on campus. It kind of made it clear there were some core rigorous ideas that everybody needs to learn. And it is things like permutation tests and bootstrap and database concepts and all. You can't get rid of that, okay? But we didn't want to then bring everybody in and keep them in that world. We wanted to feed them back out into genetics or into law or into cosmology or whatever. And that's the real picture here. It's not us trying to make them more like us. It's trying to do this feeding process. So for the professional schools, I personally just have fewer connectors, but I just take our same curriculum, the same one. Those are the core concepts, and those are hard ones, and you have to teach them. But compress that down, teach them a little faster, and then your connectors can be its management, business. How do you make a business plan based on this? How do you make a business plan that really will work in the real world? It has econ concepts, that has a, viable data model, and so on and so forth. But I would not hatch up another one. And I also, I thought you were going to talk about graduation. I won't go there, but I do think the professional is just, this is all brand new stuff, and it usually takes decades for things to get into the professional schools. But this stuff was all honed by people who've been spending time in industry. So a lot of us designed this curriculum because we knew what is being done in industry. A/B tests. Day one, they should learn about A/B tests, not about Fibonacci series in their programming course, and so on. So
we come from the same school. I have to break it to Mike that there is now a graduate certification in data science for our professional schools starting this year. And so what they're doing is sort of what you described, which is they're compressing some of our existing classes and providing some of our classes with slightly more advanced modules or modules more suited to graduate students to try to fit into their very compressed time frame. You've already talked about the connector, so I won't say that again. We have at Berkeley what are called the data science modules teams. These are teams of undergraduates who have come out of Data 8, sometimes Data 100, who work with faculty in various departments just to develop modules of data analyses in those fields. So they are working very closely with faculty and with students from other disciplines to put together these things, which are turning out to be quite valuable, I think, certainly to the students who are doing them, but also to the fields. So fingers crossed, this becomes something that we can do on a larger scale than we've been able to do before.
I guess we're going to go down the table here. So for the professional question, it's kind of a weird question, frankly, because data science is at least the way we use the term currently, that term came from industry. And it was, created because people were trying to hire these unicorn types of people who could compute and do data and all that. And so data science programs appeared initially as professional master's programs, and many of those are thriving. And so I think data science is an easy fit for a professional program or a professional school, and I think a lot of places are being very successful there. And part of the challenge there is because of success in the professional schools is getting sort of the research parts of the university to believe that it's a real field, which is why I was emphasizing that in my comments. On the question of interdisciplinary teams, I think that is a really great question. The thought there, I don't know how to do it in terms of getting the deans to give credit and things like that, which is always a challenge. But one thing I've seen work really well at our institution is problem-oriented programs. So, for example, we just finished a program on climate change where entering students were asked to start meeting, months ahead of actually showing up on campus to try to propose interesting solutions to climate change. And there was a whole set of processes that they went through in terms of trying their ideas out with some faculty who had volunteered to help them out and so on. And so I think probably the way to do it is to try to pick some of these problem-oriented topics and find a way to get people to be able to take that for credit. I mean, obviously, the things we were talking about here today, could you imagine doing one on gerrymandering, for example, right, and getting groups of students to try to work on that problem, for a whole semester together? I think it should be problem-driven.
Thanks. So in my comments, I actually somewhat ignored the fact that there are data science programs at the University of Toronto, not just statistics. They're relatively small. One of them is at the graduate level. It's housed in our computer science program. They've got a Master's of Science in Applied Computing professional master's program. It's got several streams, including a data science stream, of which the statistics department does a fair bit of the training of those students. They find it's really hard to get qualified students into that program because computer science has their kind of bare minimum requirements from a computing perspective. And so to get those who also have at least some reasonable background in statistics is challenging. So that's one of the smaller streams in that program. We also have an undergraduate program in data science that's we're doing jointly with computer science. It's new and small, so, compared to our statistics program, we're not putting a lot of students through that yet. The question of the interdisciplinary team aspect is a really interesting one, and I think it's something we don't have answers to, but we're going to have to grapple with in a really real way very shortly. I neglected to mention that we are also hiring many positions, I think 9, depending on how you count it. And one of the interesting things of those positions, both in our recent hires and the hires that we're doing now, is many of them are joint with other units. And it's not just our traditional joint with computer science or joint with math. They're quite interesting joint withs. They're joint with psychology, they're joint with the information school, they're joint with sociology, they're joint with astronomy and astrophysics, they're joint with philosophy. And it's going to be interesting. We haven't really had to grapple yet with how we're going to work these people into our undergraduate program. So I think the possibilities are actually really quite exciting when we think about how we can use these people in training our undergraduates. The connections, I've long admired the connector courses at Berkeley. I haven't figured out how we could do anything like that because we've got quite a rigid half-credit semester system. But I think we'll, by having these joint hires and thinking about creatively how we can use them, it is lots of opportunities where we're not going to have to involve the dean because it's just going to be these people we've already got already. So if you've got ideas, I'd like to hear them. I've got some that, but it's going to take some work.
Yeah, I got that
Good.
one. Thanks. Oh, yeah, so, well, I mentioned the Harvard Business Analytics program before. The Extension School has a certificate program now. We do not currently have plans for a PhD in data science, so that's a really intriguing idea. At the master's level, though, Harvard has 3 master's programs in data science, which all launched in the last couple of years. One that's joint between statistics and computer science, which is the one I'm most familiar with and that I've helped with in various ways. That part of the core of that is the course that I was describing, that turned into the full year data science sequence, and we're, again, running that as an equal partnership between statistics and CS. There's another one in biomedical informatics and another one in biostatistics. So we have a lot of different things going on at the master's level. At the undergraduate level, we don't have a data science major, but we do have a track within the statistics major, data science track, which is similar to a normal statistics major, except a little bit, more towards curated towards courses that are closer to this emerging field of data science. And about this teams question, I think that's a really interesting and difficult one that we've thought a little bit about, but don't have a great answer to. So in the data science courses that I've taught, we've emphasized group projects that are working in teams, but what you're asking about, Dustin, is more about data science working with people who know nothing about data science and how do people with very different skills work together. I don't think we've solved that at all. The only thing that I can think of in that direction is that we do emphasize communication skills, which was a big part of the modified Venn diagram, which I think was a really important addition. So we do emphasize that in our teaching, and on homeworks and projects, we'll always ask questions like, how would you explain this to your manager who knows no data science? How would you explain it, to the general public? So kind of for different questions, we pick different target audiences, and then you have to write an explanation for that. It's not just, outputting the results of your regression, right? You have to think carefully about how to communicate and visualize your results, which I think would be helpful when working on a team, but it's not the same as actually getting almost like internship experience doing that. Yeah, there you go.
So our class initially was funded by a campus-wide effort to think about ways to create really new forms of teaching across schools, and in particular ways of integrating data sciences into different professional contexts. And our experience of teaching the course very much came out of attempting to create a curriculum for journalists who had very few technical skills, and to do so explicitly in a way which wasn't going to be a sort of boot camp where they learned simply to run things in a black box, to really think, if we're teaching them for 6 hours a week in the summer, how is it, where are the moments for critical reflection? So it actually came out of, I think, the real challenge of implementing things in a very professional context with different sort of skill sets, and really leveraging that challenge as an opportunity to do something that I think befits the level of teaching that I think all of our institutions aspire to. That if we're teaching a master's degree program, it is qualitatively distinct from, say, a 6-week boot camp. In terms of team teaching, again, that I think is a profound and deep question. One thing, as I've mentioned in our class, we have sort of half and half students who come from a technical background and a non-technical background, and we every week put them together and doing things together. So, and in some cases it can be amusingly productive. So the best assignment we did all year, I think, was to have the group of 7 or so students get together and have to write a sort of rant for Twitter purposes that began with a technical development, involved tweets which would be a deep dive into technical questions, deep dives into social questions, and funny memes. And this brought together a combination of those rhetorical, domain-specific, technical sorts of things. It was kind of an amusing sort of exercise, but it really was modeling a certain kind of activity. And in terms of the assignments for the course, we quite explicitly essentially make the more humanist students do lots of problem sets, and our more technically oriented students do a lot more writing. And what this ultimately means, I think, actually, is that staffing these kinds of courses is very challenging. To staff, like, it's easy to find, in some level, people to teach the introductory material in any of our subfields. Finding people who can coordinate the teaching of teamwork, I think, is a really big problem. And we've all, I think, alluded to the kind of administrative challenges of doing that. Those are really major problems. So when professional schools have come to us and say, well, could we mount a course like yours in our school? We say, yes, you could, but you have to be prepared to hire a lot of people who teach writing. And you probably are, your deans may have other views about that.
Great, thank you. We'll get some questions. If I could just ask that they be brief, and maybe we'll just have 1 or 2 folks respond so we get more questions. So we'll start here. I've got Mercedes.
Hi, it's John Abon from the Census Bureau. I have a question that comes in the form of an advertisement. I'm not sure how many people in the room are familiar with the Civic Digital Fellowship Program. The website is codingitforward.com. It actually started at Harvard in collaboration with the former chief marketing officer at the Census Bureau. And it's an opportunity for emerging data scientists to be embedded inside a government agency for a 10-week program in the summer. They're cohorted. It comes with a $4,000 stipend and housing and meals as a part of the program. It's run in a manner that lets all the security clearances be handled before the students show up for their first day of work. So it actually works. And so that's the advertisement. And my question to all of you is, should I be advertising for other programs that have a similar goal of embedding young data scientists in real-world laboratories to do internships?
Yeah. I was going to say yes, too. Will you take Canadians? Can you take Canadians?
But what are other programs that have this flavor that you've heard about that he could be cross-promoting? I think that's the course.
There's zillions of them. There's internships galore. Surplus.
Galore.com. I've had
Data science for social good.
Data science for social good.
Yeah, data science for social good is one that's been out there for a while.
Yeah. So I'm Erica Groshin, and my question is somewhat related to John's, but one thing that I didn't hear, but I assume is in there somewhere, is a discussion of how to create really educated users of federal statistics. This is a main source of information that people will be using when they go out into the real world. So I wonder how much emphasis is there on that, and say, Matthew, when you talk about the development of data science, in some ways, the first data scientists were official statisticians, right? Trying to measure things that had never been measured before in countries. And to this day, this public good created by federal statistics is really key towards processing all sorts of other data for validation, for weighting, et cetera. So I just wanted to hear a little bit more about, is there a way that the statistical system could support you or you interact with them to clarify that role, because it's a very important part of the data science ecosystem.
Matthew, you want to give it a shot?
I mean, I could say too much about this, but the first exercise we have the students do is actually a data provenance exercise. They have to download a data set, unlike a federal one, typically badly documented and other sorts of things from the UC and Irvine site, which all of you probably use. And the students immediately we just ask them some semi-leading questions. And what they're supposed to do is think about what are the critical dimensions of the constitution of this data set, and what are the limits of doing that. So the first exercise is really a kind of literacy and interrogating kinds of data sets, and then we show them well-documented data sets, typically from government authorities, before later in the course thinking about how did that moment come about, that is a key element of the constitution of our polities, that we ought to have not just different kinds of inferential methods, but a standard stabilized set of data sources, and why does that matter to our political life? So in our sense, we do some operative stuff, but also reflecting upon the set of transformations such that became central to what we're doing, and then the way that has been contested in more sort of recent years.
Oh, yeah, just briefly, I agree that's extremely important, and for the case studies that we're developing for the new course, we do have a couple examples where we are going to be using some government data. Because it's still under development, we have to figure out exactly what percentage does what, but it's definitely an important thing that we're keeping in mind.
Since that was kind of an advertisement, I'll also respond with an advertisement. So one of our professional master's programs, to get to that question, is a program called Computational Analysis and Public Policy. It's joint between computer science and the School of Public Policy. And the enrollment in that program has been skyrocketing. And obviously, it's all based around, how do you make good policy given the availability of, or lack of availability of the good data from the government and elsewhere.
And it just, as a political scientist, one thing to point out, sometimes people think that government data is, say, just census data or just, say, elections data, but I cut my teeth on trade data, right? BEA data. And so I think helping students understand that there's a universe of data that's coming from the government, public health, so on and so forth, helps them, no matter their particular interest area, really get an opportunity. Sad Mercedes next.
Thanks, Dustin. Thanks. Actually, it's sort of a segue for this discussion on data. So since the traditional course materials were more textbook oriented, but for a course like that, we need either curated data sets or non-curated, maybe non-clean data sets that one has to clean and curate as part of the learning. So is there, are you thinking as individually in each university to create this set of teaching data sets, and is there room or some initiative that could have something shared across the university, across all these curriculums, so we have a good diverse set of quality data? Since I work on that, I would be happy to help with it. And as part related to this question, then, is also that if we want to make data science part of an academic track, we need to make count a little bit more the products that are not just publications, but are actually these data sets or software. And I know I work with Fernando Perez, and it would be a good promoter of that to say, is there code and other data science products that we're engineering, and those should be counted as part of the academic track. So otherwise, the data scientists that we're trained are going to go to industry because they will only count for that. It's a loaded question, but...
jump in there a little bit. Yeah, so all these courses in infrastructure and eagerness and energy, I hope will incentivize a lot of people out there to provide data plus inferential problems. So you may remember the Netflix prize. This is about 10 years ago. They were doing recommendation systems. It was not a standard statistical problem. It wasn't in any of the books. There was not standard methodology. And they put that out in a really interesting data set. And the inferential question was to do a good job of doing the recommendations. And that had thousands of people responding. And really interesting line of research came out of all that. And the data set was open and used and has been used and all. So I think of that as one of about 30,000 examples of people out there. So I don't think it necessarily behooves us. I really hope that we can make a platform, make it easy, work with Fernandos of the world to make it so that you can put your data there for the purposes of teaching. And here's the inferential question, here's the gotchas, here's what we like to learn and all that. That said, I also think that it behooves us to be very careful about setup. It's always not just data, it's inferential problem and data. Right? You got to be problem solving. There's a role for exploratory data analysis, but that comes much later to me. You've got to sort of, so one of our examples is just, you've got the jury composition in Alameda County by ethnicity, and you got the population by ethnicity. It's 2 columns of numbers. Are they different? And you can immediately see a freshman saying, that's an interesting question. And that's the question. Of course, the data is the data, right? But can I answer that question with this data? What does it mean to answer that question? Will someone reliably take that and use it? What are the implications of that? And so we had to kind of set up that data set and think it through and think about all the questions that students would ask and kind of go through that decision tree ourselves to think about that. And we curated. So I think there's a role for having everybody have access to all the world's data and all that, but a curation either by us or by the people out there who are real question answer to me is really, really critical. It's got to be about the problem solving as you work with data, not just the data itself.
I think the question you ask is a really important one. I've known for the past 4 or 5 years that these courses stand or fall on the quality of the example. The question has to be important. It has to be of general interest. It has to be easily explainable. The data have to be such that they are A, open. We pride ourselves on making our materials public. And B, you have to believe the model. And then the answer has to be clear enough that that it makes your point. This is all very difficult, and I'm actually going to ask Xiaoli whether the journal here can maybe, its education component, can maybe do some of this, which is taking, really key examples and very good data sets and questions and making a place where we can have a curated list for the universities of the world. Anyone really to join?
Yes. On the record. Yes. We've got another question up here, unless anyone else wanted to. We're good? All right.
Hi, I'm Debbie Sweet from Cell Press. This is a different topic, but I'm just curious. Given that you're all teaching the data scientists of the future, I'm wondering what you're seeing in terms of diversity in your class. Well, numbers of women, other types of diversity. Is that an issue? Is that something you have to work on, or is it just, I'm just curious.
The short answer is it's fantastic. It's like half women, and just diversity geographically, ethnically, by interests. I think this is the first time in my career in 30 years where I've just seen so much uptake that students say that this is really interesting to me personally. So take that problem of inequality or representation. They like that question, but they immediately have their own question, right? So that's what you want to do, is you empower them. And I think that students are so much resonating to that, and that crosses all boundaries. It is something we continue to have to work on. It's going to have to be in our attention for a long, long time to come. But I just think we're starting to build the enthusiasm, which will lead to the next wave, which will lead to the next wave. It feels like it's this cascade that is building up.
Percentage of women is increasing rapidly. Our many thousand data 8 class is about 50% women. Underrepresented minorities, ethnic minorities, is another question altogether. First, there is a relatively small percentage of them at the university as a whole. So we have programs actually that are dedicated to taking those students and making sure that they are supported and don't feel alone in these classes. And so you said, does it have to be worked on? Yes, it does. And it is being worked on. Ask us in a few years. But very, very important question. I think this is a great way to encourage students who have come from backgrounds that are perhaps not as strong in computing and mathematics, in their high schools, and bring them into those fields.
Just to follow up on that, so our experience at I guess an order of magnitude lower scale, has been very positive. I'm a computer science professor, and so for me, the diversity I see in the data science class is really just off the charts. Obviously there's room for improvement, but I think a couple key things that's helping, in addition to the things that Mike pointed out in terms of people being able to find their interests, is that first of all, the lack of prerequisites, the fact that these technical classes were developed in a way that didn't require people to already have a strong background in math or computing, I think helps a lot. And the other thing that's kind of subtle but really interesting, which is that if you take, say, the Data 8 approach, where they created their own data science library that is different than the traditional stack that people use, in some sense that kind of levels the playing field. And you don't have people coming in from high school, who had spent 3 years programming in that language. They've never seen it before. And so that makes it easier for people too, in terms of bringing in people who might not have the same background before they get to college.
We also have, I think, greater than 50% women in our statistics programs of study. They're extremely popular with our international students, these courses, so the diversity is almost flipped in some ways. The other thing I wanted to just build on Mike's previous comment is, I mentioned briefly that we're trying to code by stealth. We're quite conscious of the fact that, some math anxiety kept certain groups out of mathematical sciences in the past, and we don't want something like that to happen with coding anxiety, to be in the new flip of that. So that's an approach that we're taking, particularly in our intro course.
Great. We got another question?
Yeah. Hi. My question is about the diversity of the content offered in some of these degree programs. So obviously a lot of independently developed programs with some similarities, but also a variety, in terms of the approach, courses offered, etc. As we move forward, say several years down the road, do you see convergence, between these different programs? How do you compare it to other degree programs that have, I imagine, more similarity, like say from school to school, say in biology or civil engineering, for example?
Yeah, so who could predict the future? But I see what's emerging right now is the emergence of a new branch of engineering. It hasn't been named yet. So I think data science is as good a name as any. Other people call it AI or machine learning or whatever. It's like chemical engineering in the 40s or 50s. People had chemistry before that, they had fluid flow, they had the ability to put things together. They had no concepts of how to build a factory that made things like chemicals that were useful and economically viable. Now we're talking about not about chemicals, about people and data and computing and worldwide planetary kind of interactions based on all these sorts of things. That is fodder for a new branch of engineering, okay? And so right now we don't have a terminology for that, In fact, the word engineering is deprecated, People don't say data engineering sounds boring, genomic engineering sounds terrible, social engineering sounds horrible, right? But that's really kind of what we're doing in a positive sense. We're trying to build systems that work for people, the government, et cetera, medicine, these should be all big systems that make the world easier, more interesting, more safe, more robust, more, et cetera, more connected and all that. And it's really hard because we're seeing lots of mess up already, right? So I think that's going to take decades to roll out, just like chemical engineering eventually started to emerge in the 40s and 50s. It took some decades for it to roll out. Electrical engineering similarly, civil engineering similarly, and then back and forth with the sciences. So it's going to take decades. So ask me in several decades, I bet you by then there'll be a standardized curriculum for whatever this thing is. But we're in the very beginnings of it. So no, there's not going to be a standardized curriculum. Will there be ABAC accreditation? Will there be AP, whatever this is? But I think it's that grand effort. It's humans inventing a new kind of engineering that has to do with human beings for the first time. All the other engineers had to do with the electrons or the buildings or whatever. This is about humans, and that's why it's so hard, and that's why it needs so many people to be involved. And that's why the current curricula should be as diverse as possible. So we really explore all the different ways to think about doing this and build towards that better thing, which I hope will emerge, which will take a lot of effort.
So we have a couple more questions, and Zhao Li also has an announcement, and we have a hard stop at 6. So I'm going to propose, I'm going to take a couple questions, and then everyone gets to choose the one that they want to answer. Sound good? All right. And keep it brief.
Oh, thanks. Hi, everyone. So I'm actually a Master of Data Science student at Harvard. I took Joe's Stat 110. And I think during my summer intern at Google, although I have some domain knowledge, I sometimes still feel hard to make communication with designers, writers. So I'm wondering, I think that currently the data science program is kind of a selection bias process, because the one who want to apply data science program, they already have some computer science and a stats background. So I'm wondering, what's the better way or best way to convince different background people to learn more about data science? Thanks.
While I'm asking my question, wanted to see if it's possible to roll back to slide 32, which is going to be the core of the question. This was an Alison Gibbs presentation. Question is the following. I very much appreciate the discussion that all of you had. Several of you touched on the fundamental question of the ways in which data science may be connected in certain fashion to either the humanities or more broadly liberal education. And especially when we get to slide 32, this was the definition of adaptive expertise. It struck me as being remarkably coherent with the traditional ideal of a liberal arts graduate. And so I wanted to see if one or more of you have had, within your institutions or otherwise, have had a chance to explore that question in greater depth.
Great. And just so we have a diversity of the room over here, and this will be our last question.
Hi. So with universities and education universities, the problem is also that students don't feel necessarily prepared for the job that they're later applying for, and vice versa. Businesses feel like students are not adequately prepared for the job that they're offering. And that's in a variety of programs. So I'm curious, with the data science programs, which are obviously quite close to industry, what are you doing to ensure that the students do learn the right skills for the job they need to take later on?
Great. So you get to choose. Why don't we start at that side of the table, and we'll go on down.
Just briefly, in my day job, I'm actually a historian of the European Renaissance, so I can talk to you a lot about liberal arts education. But we actually take this question, we build it into the course, because we make the students think about what is it that distinguishes what the liberal arts, which includes mathematics in its traditional conception, from what might be, what was understood for many hundreds of years as this sort of merely mechanical. And what distinguishes it is precisely a kind of positive critical creativity. That is, that there's an ability to step back and reflect upon all sorts of practices, whether those are practices, humanist practices like philology, or mathematical practices, or other sorts of things, towards the constitution of a kind of, a critical citizen. And at Columbia, that has long been solved by a particular configuration of the core program. But we designed the course precisely to both to try to answer, to offer a critical, a liberal arts version of the course, but also to reflect on some of the questions that were just coming up about what is it that would distinguish this kind of an approach to data which has built in the sort of critical faculties, as opposed to something where it's sort of a mere cookbookery. That's actually something, and we particularly, the history of mathematical statistics in the wake of World War II is full of resonances with our current moment, of tension between mathematical rigor and domain specificity and application, and huge fights across universities that are much intellectual, as much turf fights as they are intellectual. So I think these are sort of fundamental questions. As a historian, I get to be an observer as well as a little bit of a participant, but it's a crucial set of questions, and I do think it's actually worth looking at sort of earlier iterations of some of these fundamental debates.
Joe?
So yeah, we're along those lines. We're also trying to emphasize critical thinking for our undergraduate data science courses, and we wanted to fit in with the liberal arts ideas and to emphasize thinking, not cookbook-style stuff. And in fact, a lot of students who come in from high school, many have a horrible impression of statistics as it's just, mechanically pressing buttons or doing ugly formulas with lots of square roots just to calculate the p-value, as Ron Wasserstein was talking about. There's this kind of very, very mechanical cookbook thing, and we want everything to be about statistical and computational thinking, as Mike and Ani were emphasizing as well. And then related both to that and to the question about getting people interested who have no background. So on campus, that's exactly what we're trying to do by designing this course that will have no prerequisites, and they'll have case studies drawn from many different fields so students can see that this is really, important for society, no matter what you're interested in. And, we want to have some examples from the digital humanities and many different areas. And we can also talk about online courses, and I would just point you to what Jeff Leake and Roger Peng are doing at Hopkins, and Rafa Irizarry here. We have a lot of online intro data science courses.
Alison?
I might address the skills question. I must admit that it made me a little nervous, the way you phrased it, and I may be completely misinterpreting what you're saying. But, I hear that a lot from students, too. I'm applying for these jobs, and they want me to know, and then they give the list, SQL, Hadoop, whatever. And we didn't do that. And I said, yes, but you're ready to do that. And like we tried to do a good job of training students that, it's not about the particular tool or particular skill, it's that we've taught you this general framework about thinking statistically, and we've given you the skills to learn. And then now let's talk about how you could pick that up. Our alumni are the best messengers of that. They come back in and say, yeah, I got this job, I didn't know SQL, I picked it up in a weekend because I was really prepared to do that. So I don't know if that's the kind of skill you're talking about, but our attitude is prepare them to pick up skills as they need them.
Michael?
Yeah, I guess I'll address the skills question too, just because it was the last one and it's the only one I really remember. But the answer's similar that I have. That's obviously any academic is going to give you that answer. We teach people how to learn and what the basic concepts are. An example I'll give is one of the things that we tried to move up in the curriculum compared to other things we've seen is we tried to address the issue of scalability. So you learn all this data science, you're all running it on your laptop and in a Jupyter notebook and whatever. What happens when somebody hands you a data set that's bigger than fits on your laptop and that you can handle well, in Python, for example? And so we teach Spark, because I'm partial to Spark, which is a system I was involved in. But the idea is they take a problem they thought they knew how to solve. We try to scale it up, not to industrial size, but to big enough that the way they learned how to solve it the first time doesn't work anymore. And then they figure out what breaks and how to fix it. And hopefully that's the kind of thing that'll help them, as Alison said, to learn how to learn when they get into industry.
Thanks. Oh.
Well, actually, I'm looking at the clock, and
everyone gets their chance. You can be very brief and skip if you'd like.
So I'll actually address the question of how do you, what are we doing to encourage people who are not already trained in the technical fields to go on to data science? And the one thing I would do is ask, well, why are you interested in data science? What made you interested in data science? Because I'm not going to take somebody off the street and tell them that you have to apply to a data science program, right? So the person must be thinking about it somehow. So I would ask them to try to answer that question. And then explore. So I'm delighted that Joe raised the issue of online classes. There are outstanding classes. Data 8 is online. Rafael Irizarry's Harvard class, 9 segments of it are online. If somebody plays with all of that in an informal way, then they should have a pretty good sense of whether it lights their fires or not. And if it does light their fires, and they've been through one of these programs where truly we do try to teach people how to think, then they can learn the next thing. They can learn the next system, having already learned how to think. That's the goal.
Michael?
Yeah, so I think I'll go to the liberal arts question. So Think back about 100 years, if you were around then. So there were colleges inside of universities. What's a college? It's not the same thing as a field, right? Fields are sort of departmental level, and there are communities and so on. But colleges, why do they exist? Well, it's not just to raise funds and have buildings and all that. It's because there was a moment in intellectual history where there was enough of a convergence at an intermediate level at the university that felt structurally worth exploiting. So a college in that era of biology had emerged. A college of engineering 100 years ago already existed. College of liberal arts existed. College of social sciences existed. College of physical sciences existed, right? What other new colleges do we have now on campuses? Basically the answer is not at all. I mean, everybody has a little bit. There's a professional school here or there, whatever, but there's just no other big new thing on campus in 100 years, okay? Did anything happen in the last 100 years? Yeah. Yeah, so, the emergence of computer science, the emergence of rigorous statistics and probability, the emergence of econ, emergence of information sciences, emergence...
Game theory?
Game theory, well, it's econ.
No, it's more than econ.
No, wait a minute.
Started not in econ. Doesn't matter.
David Blackwell, he was a statistician. So no, it's not these buzzwords, it's really, you gotta think up a level above that. So you gotta think about, in the last century, what emerged is taking philosophical ideas about inductive and deductive styles of thought, okay, which are back in an older tradition, and making those kind of actionable in the real world. And including, so in fact, what I made the little pitch a minute ago about the engineering thing that's emerging, I do believe that's not all of what's happening though, okay? That's a big part, that's a big new important thing. But bigger than that, I mean, someone who's doing data collection for doing physics is not doing that, but it's bigger. So I actually think this is the right level of data science. It's not a field. It's not an emerging field. It's an emerging college level thing. And that's what Berkeley finally did. So I spent 5 years of my life fighting deans, and they were awful, just to say. And none of them wanted this college. Every single one of them, they were awful. All but one. All but one. Well, one of them kind of let it to happen, but the others just did not want it. No one stood up and said, yes, make it happen, right? So they all eventually got put out to pasture, and we won at that point, okay? And we, being all the faculty, bottom up, who realized this was obvious. All the education reasons, all the research reasons, and so on. But we got what we wanted, which is a college, and we now have a great dean, Jennifer Chase. I believe in her, she's great. But that's what the level you want for this thing, because it's that big. So that is the liberal arts. So I think liberal arts emerged when there was an era where it was like, hey, all of human knowledge, the Enlightenment and all, it's come together in this thing that everybody should kind of resonate to. It's not everyone on campus in some sense, but it's a core thing that universities do. And it's kind of shocking to me that in 100 years, nothing has happened like that. I think this is it. Okay, this is the first time I've seen almost everyone on campus agreeing something's happening. And I don't think it's a new field. I really don't. I think the principles were already there, and there's an engineering side to be built. But it's rather this thing that's more vague in some level, but it's the college level. So I'd encourage those of you who in your own universities feel that might be right to go do it, because I think if we do it in about 5 or 6 universities, it'll take over. And that will have more impact than any other thing we've talked about here today. That every university has a field as it needs to have the information, decision, ethical, philosophical, sciences, whatever you want to call it, all together. That would change human history.
Thank you. Well,
I'm going to add.
Oh, sure. Go ahead. Go ahead.
Mike said from the bottom up, from the faculty, right? It's from the bottom up from the students. Listen to your students. They demanded it. And finally it happened.
Well, Berkeley should debate about that.
No. But
they came, but the faculty have to lead here.
No, of course faculty have to lead, but the students want it. The students really want it. That's why we're here. That's why we're having this conversation.
The deans eventually tell them the students want it. That is your argument.
Great. Well, I think we as a crowd owe you guys a big round of applause, and thank you for your perspective. So to close things up, Jali has a couple of brief remarks, and I'll hand it over to him. Oh, yeah.
Thank you all. I know it's really late, but I'm going to deliver about 1 hour closing remarks just to make everything. All right, I got your attention. All right, okay. So first I want to say that for putting a meeting like this together takes really, really a lot of work. And I really want to invite Liz, Kevin, Jamie and all the staffs that stand up, that we can give you a round of applause. Just. Second, that this morning I said I'm going to give this to person, ask the best question, and then finally I realized that the students was asking question, and we do everything for the students, so I want to give to this wonderful student who asked the question. Thank you. Come here. Now here's my 1 hour closing remark. Okay, stop me anytime. There is a saying often attributed to Chinese. May we live in an interesting time. Now, as a Chinese, I can tell you, I've never heard of that phrase in China. And I'm quite sure most of my Chinese friends said, we never heard of it. But the truth is, we are living in not just an interesting time, we're truly living an exciting time. In fact, as someone today said, we're living a sort of a historical moment. And I want to give a specific example today, really relate to everything happening today, and what kind of historical moment we're living in. Today, we talk a lot about how we're using the 1940 census to study about the differential privacy impact 2020 is coming. Now, for those of you, I know many of you who were not born, not like me, before 1940, that 1940 was the first year the idea of sampling survey was implemented by the U.S. Census Bureau and the leadership of Morris Hanson, who was John Ebbau's predecessor like 80 years ago. And that was pretty much the concluding part of what being regarded historically as the intellectually violent revolution. Let me explain what that meant. Because the idea of using survey sampling in this national scale was not a new idea back in 1940. It was actually proposed by the founder of Statistical Norway back in 1895 in International Statistical Institute Congress meeting. When he proposed that idea, I think his name is Adhikari or Kia, can never pronounce correctly, it was shocking. Think about like anybody at that time proposed idea that you can learn 100 million people by just study about 100,000 or maybe even just a few thousand people. That was just unbelievably sort of a novel and seems completely radical idea. It took literally about half a century for that idea to gradually kick in until the Census Bureau put that thing in the database. It pretty much become the standard of all social science. We do that all the time. So I think what we're witnessing now, the 2020 census and the leadership of John, is what I would regard is going to be the second intellectually violent revolution. Because we debate all of this in today's, like how these data will be used or not used, all the problems. But the truth is, when the data are there, with all the differential privacy there, we have to all learn how to analyze them. It's going to really sea change how we think about those things. And I also want to mention that there was a very interesting thing happened today. We talk a lot about this afternoon about the gerrymandering, right? And we talk about the impact of the differential privacy on the gerrymandering. As I was thinking about it, I realized, many of you probably remember this morning, Robin showed that the mathematical results that when you have differential privacy data on both the X variable, Y variable, what's going to happen is it necessarily reduces the slope, right? Because intuitively, their correlations adding, it reduces the slope. But if you think about the implication for the gerrymandering, gerrymandering is a form is trying to seek the maximum correlation between sort of the voting behavior and the outcome, right? So when I think about that way, is it possible that actually by injecting all this noise into data in that content, probably going to reduce the effect of gerrymandering? Because people are going to gerrymander according to the data they have. If they don't correct it, I think that the effect may not be as strong as they actually believed. And I think that probably will be something quite interesting to study. So the reason I mention this is there are just so many things happening now, and it's a truly, truly exciting time. And I think I'm really glad that we have the opportunity to contribute to that exciting time by creating Harvard Data Science Review. Obviously, I have to turn back into this whole Harvard Data Science Review. And I really want to invite everyone to be a writer, a reader of the Harvard Data Science Review, because our mission and the goal here is that this is the place to go if you want to know anything about about the data science. And I think today's meeting just gives us a very small examples, all the exciting things that happen. I just want to mention that, as I said, it's going to 1 hour, so I'm going to mention more stuff that in the future issues that we will be talking about. January issue, the whole topic of what they call the algorithm politics, which is including the algorithm fairness, accountability, transparency, bias, all these issues. And I think in the April issues, it's going to be on the reproducibility and the replicability of science. That's another big topic. Then we would having the July issues on this, pretty much on what we talk about today. There's a computational social science issue. And there are all sorts of things about, for example, cybersecurity, individualized medicine, you name it. There are just so many topics that we all can be related to. And I really want to echo what Mike Jordan said about we are really at this college level. This is the same message that I've been trying to deliver as well. I was at the university in Canada. I'm not going to mention the name because I'm actually encouraged them to really think about college of data science. As Mike is absolutely right. Berkeley already started. We just take it, and this is one of the things that take a small sample. Take a 5/6 of university started, everybody else will follow. And that will be truly a sea change. Who knows? Someday you may even see a University of Data Science. That might be too much, but with that, I'm going to closing this symposium and thank you all for coming today.